Hello, this is Jude Socrates, and welcome to a portrait of linear algebra. In our last video, we talked about the concept of diagonalization. So today, we are going to relate the concept of diagonalizability to the concept of what are called multiplicities. So of course, we're going to start there. We will define the concepts of algebraic and geometric multiplicities. So there are two of them. And we will learn the relationship between these two multiplicities. We will prove a theorem relating these two multiplicities to the concept of diagonalizability. So let's begin by defining the concepts of algebraic and geometric multiplicities. Suppose that A is an n by n matrix with distinct eigenvalues, lambda 1 through lambda k, and we are going to allow the possibility that the eigenvalues are imaginary. In other words, they're not real numbers. Suppose that P of lambda factors as lambda minus lambda 1 to the power n1 times lambda minus lambda 2 to the power n2, and so on, up to the last eigenvalue, lambda minus lambda k to the power n sub k. So what should happen to these exponents, right? We know that A is an n by n matrix. So the highest term in P of lambda has to be lambda to the n. So the sum of these powers must be equal to n. We call the exponent n sub I the algebraic multiplicity of lambda I. And we call the dimension of the corresponding eigenspace for A with respect to lambda I, the geometric multiplicity of lambda I. We will agree that this dimension will be 0 if lambda I is an imaginary eigenvalue, at least for now. So there's something a little mysterious about this caveat. If you read chapter 10, perhaps at the end of this course, the easy thing to do is to extend the concept of Rn to Euclidean spaces over complex numbers, imaginary numbers. So there, we will allow eigenvalues to be imaginary, and of course, the eigenvectors will also contain imaginary components. Okay, so in this theorem, we see the main relationship between these two kinds of multiplicities. For every eigenvalue lambda I of our n by n matrix A, the geometric multiplicity of lambda I is at most the algebraic multiplicity of lambda I. So, in other words, using the notation that we had in our previous definitions, the dimension of the eigenspace for A with respect to lambda I has to be between 1 and n sub I. It's an eigenvalue, so therefore there's at least one eigenvector, and eigenvectors are not allowed to be the zero vector. So therefore the dimension is at least 1. There's at least one non-zero vector in the eigenspace. Okay? But the exponent of lambda minus lambda I in the factorization of P of lambda is what controls the upper bound of this dimension. You cannot exceed that power. Now, what would happen if the power is exactly 1? So in other words, you have a simple root for your characteristic polynomial. Well, let's see how many numbers are between 1 and 1, exactly 1. So therefore, the dimension of that eigenspace has to be exactly 1. Okay? So here is an 8 by 8 matrix, and actually I'm not going to show you what's inside the matrix. What's important is the factorization of its characteristic polynomial. Okay? So, does it add up correctly? We have a power 2 over here, power 1, power 3, and power 2. So 2 plus 1 is 3, plus 3 is 6, plus 2 is 8. Okay? So this is a possible factorization for the characteristic polynomial of an 8 by 8 matrix. Okay? So we talked about power 1. What if it's a simple root? So lambda minus 5 is an example of a simple root. And it's the only simple root for this P of lambda. Okay? So what we're going to do now is, let's see what this theorem says about the dimensions of these eigenspaces. Okay, so I have prepared our notation, of course. Our eigenvalues are -3, +2, 5. And for lambda squared plus 4, that doesn't factor over the real numbers. The roots are imaginary. Okay, so you have 2i and -2i. So I hope you remember your algebra. Okay, so we said that if your eigenvalue is imaginary, then sorry, but our dimension will be exactly 0 for those eigenvalues. Okay, all right, so what else did we say? If the power is 1, then the dimension will be exactly equal to 1. Okay, so these two, of course, fall under the general conclusion of this theorem. This eigenspace, the eigenvalue has power 2 in the factorization, so the dimension is at least 1 and at most equal to 2 for that eigenspace. Okay, and for this eigenspace, for lambda minus 2, it's also again at least 1 dimensional, and this time at most 3 dimensional. So I said in our goals that our third goal is to connect the concepts of algebraic and geometric multiplicities to the concept of diagonalizability. Okay, so if we want a matrix to be diagonalizable, we need a lot of eigenvectors. Okay, we need n linearly independent eigenvectors, where A is an n by n matrix. Okay, so towards that end, okay, we're going to start with this kind of baby step. Okay, so this is about the independence of eigenvectors from distinct eigenspaces. Suppose that lambda 1 through lambda k are the distinct real eigenvalues for an n by n matrix A. Okay, so let's not mess around with imaginary eigenvalues, at least for this chapter. And let's suppose that b sub I is an eigenvector for A that corresponds to the lambda I. Okay, so you have an eigenvector for each of these distinct eigenspaces. Let's put those eigenvectors b1 through bk into one set of vectors. Then this set is linearly independent. Okay, so hence the title of the theorem. So if A has a total of m distinct real eigenvalues, then at the very least, we can find m linearly independent eigenvectors for A. So in our last example, and no, it wasn't 9 by 9, it was 8 by 8. Okay, how many distinct eigenvalues did we have? How many real distinct eigenvalues? That's real, that's real, that's real, imaginary. Okay, so we have 3 distinct eigenvalues. Each of those eigenspaces is at least 1-dimensional. We don't know if this one is 2-dimensional or this one is 3-dimensional. So according to this theorem, we have 3 distinct eigenvalues. So we can find at least 3 linearly independent eigenvectors. Okay, so sadly for this matrix, we already know that it's not diagonalizable because we have these 2 eigenvalues which are imaginary. Okay, so at that point, it's game over for that matrix. All right, so this proof is going to be through mathematical induction. Okay, and maybe you remember what it is. You saw it in pre-calculus, or at least in most pre-calculus classes. But just review. Okay, there are basically 3 steps to induction. Okay, you prove a statement when n is 1, and then you write the inductive hypothesis, or the induction hypothesis. Okay, you assume that what you're trying to prove is true for some n equals j. And the hard part is in the inductive step, where you prove that the property that you want to show is proved when n is j plus 1. Okay, so I do have this n equals 2 step over here. I wanted to include it as a little bit of a bonus, okay, because it's a little bit of a jump sometimes when you go from 1 and then you jump it to j and then j plus 1. Okay, so let's take a baby step from 1 to 2. Why not? All right, so if you only have one eigenvalue, the theorem is asking you to show that a set of one vector, one eigenvector, is linearly independent. Okay, but we mentioned that eigenvectors are not allowed to be the zero vector. Okay, so V1 is a non-zero vector. All right, so a set with any non-zero vector is automatically linearly independent. So I hope you remember. I think we saw that all the way back in chapter 1, or if not, at least early chapter 2. Okay, so baby step. Suppose now you have 2 eigenvectors, but remember they have to come from distinct eigenspaces, different eigenspaces. We want to show that those 2 eigenvectors form a linearly independent set. Okay, but what do we know about sets containing 2 vectors? So they make an independent set if and only if those vectors are not parallel to each other. Okay, well, they're from distinct eigenspaces, so they can't be parallel. Okay, so now for the induction hypothesis, let us assume that the set from V1 through Vj is linearly independent for some positive integer j. Okay, we can make that statement because we already did the case when n equals 1 and n equals 2. So this is definitely true for V1 or V1 and V2, but let's assume we have proven it for V1 through some Vj. Okay, so the hard part, where all the hard work of induction goes into, is we now have to prove the step for n equals j plus 1. Okay, so that means that if we include one more vector into this set, so we already have v1 through vj, what if we throw in another vector vj plus 1? Then that bigger set, that extended set, is still linearly independent. So this is the statement that we prove. Okay, there's a bit of writing that we have to do for this proof. So I have written the steps so far. Okay, so because we want to show that the set is linearly independent, we have to set up the dependence test equation. So the linear combination C1 V1 through Cj plus 1 Bj plus 1 has to be the zero vector. We have to prove that all the coefficients C1 through Cj plus 1 have to be 0. Okay, so maybe we should write that down. Show that C1 through Cj plus 1 all have to be 0. That's our goal. Okay, so here's the battle plan. We are going to do two things to this equation, right? Let me show you the first thing. We will multiply both sides of this equation by the matrix A. Okay, so A times this linear combination right over here must be equal to A times the zero vector. Okay, but of course we know that the right side is the zero vector. Okay, so next let's use additivity. Okay, we can distribute A to each of these terms. Okay, so yeah, strictly speaking, I guess that should be A times C1 V1. Okay, but we have the associativity property, also known as homogeneity. So we can take the C1 out and have C1 times AB1. Okay, and similarly C2 times AB2, and so on. Okay, so you get the coefficients in front where they belong. Okay, but now the magic step. Each of these vectors are eigenvectors, and the corresponding eigenvalue has the same subscript. Okay, so AV1 has to be lambda 1 V1. AV2 has to be lambda 2 V2, and so on. Okay, so starting with this dependence test equation, we get this new equation. Okay, does that tell us that all of these coefficients are zero? Not yet. Okay, so what are we going to do? We need to use the induction hypothesis somehow. Okay, the hypothesis said if you only have C1 through C1V1 through CJVJ, and that's equal to the zero vector, then yeah, all of these coefficients have to be zero. Okay, but unfortunately we have one more vector. So there's nothing that tells us that, oh, these are zero. No, this is a new dependence equation, test equation, involving more vectors. So we can't say right away that those coefficients have to be zero. Okay, no wishful thinking. Okay, but what are we going to do? We want to get rid of this last term, the one with the dj plus 1. Okay, if that weren't there, we kind of erased all that part. Oh, okay. So now maybe I can say something. Okay, because oh wait, can I say something? No, the eigenvalues could be zero. Okay, one of these eigenvalues could be zero. Okay, so what is the other thing, the second thing that we're going to do to this test equation? Well, we want to get rid of the last term, right? So if we multiply both sides of the test equation by what's missing, lambda j plus 1 is missing. Okay, then we can now subtract those two equations. Okay, and then maybe something nice will happen. All right, so that's the second thing we're going to do. Multiply both sides of this test equation by lambda j plus 1. All right, so now I can start scrolling. So multiplied by lambda j plus 1, you'll get lambda j plus 1 c1 b1 after you multiply that through. But like before, we put c1 ahead. Okay, so lambda j plus 1 c2 b2, we write that as c2 lambda j plus 1 b2, and so on until we get to the term that we wanted. And of course, if you multiply the zero vector by any scalar, you still have the zero vector. Okay, so what we're going to do next is we are going to subtract this last equation from this second equation. All right, so this is the equation that we got after we did the first thing, which was multiply both sides of the test equation by a. And this was the equation that we got after we multiplied the test equation by lambda j plus 1. So now we subtract. Okay, so I guess subtract the second equation from the first equation. Doesn't really matter which order it is. So we have a common factor of c1, but we have lambda 1 minus lambda j plus 1, common factor of b1. Okay. Similarly for b2, we have c2, common factor, lambda 2 minus lambda j plus 1, and so on. Okay, so that last term disappears to cancel each other out. So before that, the last surviving vector is vj, and the coefficient is cj times lambda j minus lambda j plus 1. Okay, now we can use the induction hypothesis. We have a test equation involving only v1 through vj. Okay, so since our set of vectors v1 through vj is independent, then we can now conclude that c1 through cj, all of those coefficients have to be, oh, wait a minute, not too fast. The coefficient of v1 is not just c1, we have c1 times lambda 1 minus lambda j plus 1. Okay, so after we did step 1, I said, oh, wait a minute, these eigenvalues could be 0. At least one of them could be 0. But now we have a different looking equation. Okay? Can lambda 1 minus lambda j plus 1 be 0? No, because our eigenvalues are distinct. Okay? So lambda 1 is different from lambda j plus 1. Lambda 2 is different from lambda j plus 1. All the way down to lambda j has to be different from lambda j plus 1. Okay? So now we can conclude that these coefficients have to be 0. And that is because lambda 1 is different from lambda j plus 1, and so on. Okay, so therefore, those coefficients have to be 0, and before we celebrate and say, oh, we're finished, there is one more coefficient, cj plus 1. Okay, but if these coefficients have to be 0, then we only have one vector left in our test equation. So the test equation simplifies to the last vector times cj plus 1 has to be the 0 vector. Oh, wait a minute. When is a scalar times a vector equal to the 0 vector? Remember, we have the 0 factors theorem for vectors. Okay, either the coefficient is 0 or the vector is 0. Okay, again, we have an eigenvector though, so vj plus 1 cannot be 0, so cj plus 1 has to be 0. And that completes the proof. All coefficients now from c1 all the way through cj plus 1 have to be 0. Alright, so now we get to the main theorem for this video, and that is the multiplicity test for diagonalizability. We saw in many of our last examples over the last 3 videos that there are some matrices. I believe our earliest example was of a 3x3 matrix where we had a double eigenvalue and a simple eigenvalue. Okay, so one was power 2, one was only power 1. Okay, the eigenvalue which had the square acted a little strange. Okay, in some matrices that eigenspace was 2-dimensional, In some, it was only one dimension. Okay? So now we know that 2 is not a coincidence. Okay? That eigenspace can be at most 2-dimensional. Okay? So there is absolutely no hope that we will get a 3-dimensional eigenspace if the power is 2, but there is a possibility that the eigenspace is only 1-dimensional. Okay? Could be less than 2 in dimension. Okay, so now we're going to find out that the only way for a matrix to be diagonalizable is to have the dimension of the eigenspaces to be as big as they possibly can. Okay, so here's how to say it more precisely. Suppose you have A to be an n by n matrix, then A is diagonalizable if and only for all of its eigenvalues, lambda I. The geometric multiplicity of lambda I, meaning the dimension of the eigenspace, is exactly equal to its algebraic multiplicity. Okay, so in all fairness, we are not going to give a general proof for this theorem. We're going to give you the idea though. The problem with the general proof is that the notation gets messy. Okay, so I'm going to keep it simple with just a demonstration on this maze. So let's start off by playing the same game that we did for our last example, which was 8 by 8, I believe. Okay, so this is now a characteristic polynomial where all of the roots are real, all the eigenvalues. We have -4, +3, and +6 as our eigenvalues. Do the powers add up correctly? That's a 2, that's a 1, so 3 plus 4, 7. Okay, so this is a possible factorization for P of lambda if you have 7 by 7 matrix. What can we say about these dimensions? Using the algebraic versus geometric multiplicity theorem. So the lambda equals -4 eigenspace is at least 1-dimensional before, but it is now at most 2-dimensional. Okay? So similarly for lambda equals 3, oh wait, no, not quite similarly, we can say something more. Because that power is exactly 1, that dimension is exactly 1. Okay. The lambda equals 6 eigenspace is at most 4-dimensional. So that is less than or equal to 4. And of course, it is at least 1-dimensional. Okay. So at this point, that's all that we can say about this 7 by 7 matrix if this is its characteristic polynomial. Alright, so now we are going to prove this theorem for this 7 by 7 matrix. When will it be diagonalizable? So it's an if and only if theorem. There are 2 directions that we have to show. Forward direction, we are told, let's go to this here. We're told that A is diagonalizable. We have to show that each geometric multiplicity has to be equal to the algebraic multiplicity. Okay, so that is what we have to do for the forward direction. Okay, so let's write down, let's do both of them. Okay, what does the given say? Okay, so let's dig a little deeper. When is a matrix diagonalizable? It's a 7 by 7 matrix, correct? So we should have 7 linearly independent eigenvectors for this matrix. So the given says that we have a set S, magic, B1 through B7 of linearly independent vectors. Okay, and I'm not hiding. Okay, so what do we have to show now? We have to show that each of these geometric multiplicities, their dimension, must be exactly equal to the algebraic multiplicities, which are the upper bounds. Okay, so we must show that the dimension of the -4 eigenspace is exactly 2. Okay, we have to show that the 3 eigenspace is exactly 1. We already know that. Okay, and finally, we have to show that the last eigenspace is exactly 4. Okay, so that is what we have to show. Okay, so what we're going to do is kind of cute. I like this method of proof, okay, because it's kind of like trying to fit 7 objects into 3 boxes and making sure that you have a snug fit. Okay, so what do I mean by that? What do these 3 boxes represent? Okay, well, they will represent a basis for each of the 3 eigenspaces. Okay, all we know right now is that the first eigenspace is at most 2-dimensional. The second is at exactly 1-dimensional. We at least know that. And the third is at most rather, 4-dimensional. Okay. So, what do I mean by fitting things into boxes and a snug fit? Okay. So, is it possible that the dimension of the first eigenspace is smaller than 2? Okay. We know it's at least 1. Okay. But what if we can't have a second basis vector? What if there's only 1? Okay. So now comes the part about fitting these 7 vectors into these 3 boxes. Okay. Now why can we do that? We know that these 7 vectors are all eigenvectors, and in fact they're independent. Okay. So what does that mean? Well, where am I going to put V1? Okay, so maybe it belongs in the third eigenspace. Okay, these are just randomly numbered eigenvectors. Okay, where is V2 gonna be? Okay, maybe it's in the second one. Okay, what about V3? Okay, how about it's in third again? And how about V4? Okay, maybe it's in the first eigenspace. Okay, what about V5? Okay, I'm running out of room. Okay, I said that I only have a 1-dimensional subspace for lambda equals -4. The lambda equals 3 eigenspace is exactly 1-dimensional. So yeah, there I cannot put V5 in there because there's only room for 1 eigenvector in the basis. Okay, so V5 has no choice but to be there. You see what I'm saying now about the snug fit? Okay, where's V6 gonna go? No room here, no room here. It's gotta be over here. Oops, you ran out of room. Okay, there's no room for the last vector, V7. Okay, so this is a contradiction. Okay, so what this means is that thus the dimension of the -4 eigenspace is exactly 2. Okay? So now that we know that, we can also use the same kind of reasoning to show that the 6th eigenspace is exactly 4-dimensional. Okay? Exactly the same logic. So what if it was less than 4-dimensional? In other words, I'm going to burn that last space. Okay? Play the same game. All right? So we already know that the first eigenspace is exactly 2-dimensional. Okay? So we have room for 2 in the first basis. Okay? play the same game. Where is V1 going to go? Maybe in the third. Where will V2 go? Maybe in the first. Where will V3 go? Maybe in the third. V4. Okay, how about over here? V5. How about over here? See where this is going? V6. I am out of room here. I am out of room here. I can only put V6 over here. And once again, there is no room for V7. So, similarly, the dimension of the eigenspace for lambda 6 must be exactly 4. Okay, so I erased our diagrams over here because I want to now outline what we have to do in the backwards direction. So this time, our given condition is our conclusion, and what we wanted to show in the forward direction is now our given condition. Okay? So if the geometric multiplicity of each lambda I is exactly equal to its algebraic multiplicity, we have to show that A is diagonalizable. Okay? So basically, we are also going to switch what we have over here. So this time, the given says that these dimensions are exactly what we want them to be. They can't be smaller than those numbers. And now what we want to show is that we have set S made of 7 linearly independent eigenvectors. Okay, so the given and the conclusions change roles. Okay, so that is going to be our job in the backwards direction. Okay, so this is how the proof is going to work. We are told that these dimensions are exactly 2, 1, and 4. So therefore, the first eigenspace has a basis made of 2 vectors, 2 eigenvectors. So let's call them V1 and V2. Okay. Similarly, this eigenspace for lambda equals 3 is exactly one-dimensional. So let's make a basis for it. 1 eigenvector. Okay. Finally, for the last eigenspace, lambda equals 6, it's supposed to be exactly 4-dimensional. Okay, so let's make a basis for it made of V4, V5, V6, and V7. Okay, and again, we can do all of that because we are given that these eigenspaces have exactly those dimensions. 2, 1, and 4. Oh, how many eigenvectors do we have? We have 7 of them. Okay, so what we have to show is that these 7 vectors form a linearly independent set. A couple of theorems ago, we saw a theorem that said that if you have m distinct eigenspaces, then you are guaranteed that you will have m linearly independent eigenvectors. Okay? So what the theorem told us, okay, pick one vector from this eigenspace, one vector from this eigenspace, one vector from this eigenspace. Those 3 eigenvectors will be linearly independent. Okay, now what about the other 4? Okay, so this is, I like to think of it as a greedy theorem. Okay, it wants all 7 of them. Not just one here, one here, one here. Oh, please. I want all 7 of them. I'm hungry. I want all 7 of them to be linearly independent. Okay? So that part is not very obvious at all. 3 of them, maybe, but not all 7. Alright, so remember how I said in that previous theorem that it's going to be like a baby step towards our main goal. We are now in that main goal. Okay, so in that baby step, we use the principle of mathematical induction. Okay, if you already have j independent eigenvectors and we add one more, then that set is going to remain independent. Okay, but this induction is going to be different. Okay, it's also going to be like a greedy version of that induction. So instead of adding just one vector at a time, we're going to add all the basis vectors from the next eigenspace. Okay, so there will basically be 3 steps in this induction. Okay, so forget about j as well. 3 steps. Okay, so those steps are, well, let's start with not just b1, but b1 and b2. Okay, prove that that set is independent. So yeah, I should include the word prove in this sentence. Okay, but wait a minute. A basis, that's the definition again. A basis spans our subspace, but is also linearly independent. So, step 1, no problem. A basis has to be independent. So, the set is independent. No work at all. Okay? So now, we are going to add to b1, b2 our next basis. Oh, but there's only one vector. Okay? So fine. We have 3 vectors now. We want to show that that set of 3 vectors is still linearly independent. Okay? So the idea is basically the same technique that we used in that theorem with bj plus 1. So, assemble the test equation. C1 b1 plus C2 b2 plus C3 b3. So let me copy that here. Plus C2 b2 plus C3 b3 has to be the 0 vector. Okay, so it must be the 0 vector. Where are we? R7. Okay, so remember the 2 things that we did to this test equation. Okay, the first thing was multiply both sides of that test equation by the matrix A. Okay, left side, right side, multiply by A. Oh, but that's still the 0 vector. Okay, now what? We use additivity, homogeneity. So we get C1 AB1 for our first step. Okay, that's right. C1 AB1 plus C2 AB2 and so on. So there will be an A there, there will be an A there, and we still have the 0 vector. Okay, but now, what do we know? V1 and V2 are eigenvectors for lambda equals -4. Okay, so therefore, AB1 must be -4 V1. Okay, so we will replace AB1 with -4 V1. And similarly, AB2 we're going to replace with -4 V2. Now what about V3? Its eigenspace is for lambda equals 3. So that should be 3V3. Yeah, there we go. Okay, so that step is possible because the eigenvectors come from these eigenspaces. Okay, so these are like the lambda 1, lambda 2 to lambda j, except now we have the same lambda for the first 2 vectors. Okay, but now, what was the other thing that we did to the test equation? We said, I want to get rid of the v3 because if I only have v1 and v2, I know they're independent. Okay? So now we can multiply both sides of this equation by 3. Okay? So, but also we have, let me copy this, and multiply all of them by 3. Okay? So let me put the 3 next to the v1 and the v2 and the v3 so that it looks just about exactly like what we have in this last equation. Okay, so those two terms now match perfectly. And of course, 3 times the 0 vector is again the 0 vector. Okay, excellent. But now what are we going to do? Okay, so we said next step, subtract. Okay, so if we subtract this equation, let's say from this equation, I think it will look nice so that we get 3 plus 4 or 7 v1. Okay, subtracting, we get, okay, so the first two terms will survive. Whoops, we pasted the wrong thing. These guys. There we go. So 3 plus 4, 7v1, 3 plus 4, 7v2. The v3s will cancel. Okay, so we get on the right side. Now we want the 0 vector. Okay, so according to k equals 1, these two vectors are independent, so therefore c1 and c2 must be 0. Okay, so since v1, v2 is an independent set, c1 equals 0 equals c. Okay, so back to this test equation. These two coefficients are 0. We are left with that. Sounds familiar? We are left with c3, v3 is a 0 vector, and so c3 equals 0 as well. Again, v3 is an eigenvector. It's a non-zero vector. So therefore, it must be c3 that is 0. Okay, we are ready for the final step in this induction. At this point, we have achieved k equals 2. So let us write that here. At this point, we have shown that this set of vectors is still linearly independent. Okay, so now we have to show that those 7 vectors, all 7 vectors, still make a linearly independent set. Okay, not gonna lie to you, I paused the recording because it takes some effort to write out this test equation. Okay, so we now have 7 vectors, 7 coefficients. We have to show that all 7 coefficients must be 0. Okay, but it's exactly the same idea. We will multiply both sides of this equation by 8. Okay, so copy that. 8 times all of this must be equal to 8 times the 0 vector, which, once again, is just the 0 vector. Okay, so we are going to distribute A to all the 7 terms of this test equation. Okay, so remember that v1 and v2 are from the first eigenspace for -4. v3 is for lambda equals 3. The last 4 are for lambda equals 6. So let me pause again, and I will distribute that and include the last. Okay, so aside from setting up the new equations, I also copied our directory over here to remind us that the first two vectors have -4 eigenvalue, the third one is 3 eigenvalue, and the last 4 now have 6 as their eigenvalue. So therefore, this becomes 6 V4, and this is also 6 V4, and 2 more. Last one. 6 V7. All right, so what's the second thing that we're going to do? We're going to multiply both sides of this test equation by the last eigenvalue. Okay, so notice that something different is happening for k equals 3. When we had k equals 2, we only had one extra vector. Okay, so we multiply both sides of the test equation by the last eigenvalue is 3, and only one eigenvector canceled, got eliminated. Okay, this time we have 4 eigenvectors which have the same eigenvalue. Okay, so therefore we are going to multiply both sides of the original test equation by the last eigenvalue, which is 6. Okay, I'm just going to write 6 over there, and they should have parentheses, but let's not bother. Okay, because what we're going to do next is we're going to subtract this equation from this equation. Okay, and of course 607 is still 07. Don't waste time. Okay, so now the last 4 vectors are going to get canceled, and we only get as our survivors the first 3 vectors. So subtracting, we only get these 3 vectors have to be sum up to the 0 vector. Oh, wait a minute, I again cut and paste fail. There we go. Okay, so 6 minus negative 4, that's not now going to be 10v1. 10v1, 10v2, and 10v3. Oh, I'm sorry. 6 minus 3, not 10. So, yeah, the v3 has 3 here. 6 minus 3. That should only be. Okay. But the same idea. Okay. The coefficient of v1 is 10c1. 10 is not 0. So c1 must be 0. c2 must be 0. And c3 must be 0. Oh, why? Because we have shown in k equals 2 that those 3 vectors are linearly independent. Ah, so by step k equals 2, c1 and c2 and c3 equal 0. Okay, shall we celebrate? Almost there. These 3 terms are now 0, so we still have these 4 terms. Okay, so the test equation now simplifies to that. Okay, only the last 4 terms. Oh, but wait a minute, v4 through v7, those are your basis vectors for the last eigenspace. Okay, so, but since v4 to v7 is independent, then c4 through c7, let's stop messing with it. All have to be 0. Okay, so there you go. Mission accomplished. c1 through c3, and now c4 through c7, all have to be 0. We have shown that v1 through v7 is still linearly independent. Okay, and of course we wanted to do that because now we have 7 linearly independent eigenvectors, we have a 7 by 7 matrix, and so we can put together those 7 eigenvectors into a single matrix. That matrix will be invertible because the columns are independent, and therefore our matrix A is diagonalizable. Okay, before we say goodbye, I forgot to mention something in our last video in my excitement to show you what happens to these 3 very special matrices. What did I want to show you? In general, we know that matrix multiplication is not commutative. Okay? If you change the order of the factors, you may not get the same answer. Okay? But what we did in that last video was, given the 3 matrices for projection onto L and projection onto pi, so it's actually just the middle matrices which have those labels. We conjugate by C on the right, C inverse on the left, and we got these 3 diagonal matrices. Okay? Now, why is this a big deal? Okay? What we did is a process called simultaneous diagonalization. It is in the very last section of the 4th division. Okay? And something that I'm very proud of. You don't see it very often in introductory linear algebra textbooks, but it's something you can do. Okay, so let's start with these diagonal matrices. Okay? Those are easily seen to be commuting matrices. So what does that mean? If I multiply these 2 in this order, we're going to get this. Oh, that looks familiar. Oh, it's just that second one. If we multiply them in the reverse order, now it's not obvious that we should get that second one. Oh, but we do. Okay? As a matter of fact, it doesn't matter what is in these diagonal matrices. Change. 12, 70. Okay, we have these 2 diagonal matrices. Guess what? Oops. I need to highlight both of them. There we go. Negative 12, positive 60, 8 times 7p. When you multiply diagonal matrices together, all you have to do is multiply the diagonal components. So we get, boom, exactly the same matrix. Okay? What is not obvious is that if you multiply these 2 matrices, again, it doesn't matter which order of multiplication. You put them in, you'll get the same answer. Okay? Promise. First, 2 copies. Second matrix. Okay? So that starts with 61. This starts with 57. Put it on the right. Put it on the left. Okay? What do we get? That's not the first matrix, is it? No, it's not. Completely different. Maybe it's the projection on L. No, it's not the projection on L either. It's something completely different. Okay, what if you reverse the order? Still exactly the same. Okay? So this is the main theorem on simultaneous diagonalizability. Okay? That if you want 2 diagonalizable matrices to be simultaneously diagonalizable with the same invertible matrix, then they have to commute with each other. In other words, A times B and B times A must be exactly the same. And it happens to be an if and only if statement. So if those 2 matrices commute with each other, then you can actually find one invertible matrix C that will diagonalize both of them. Okay? So obviously this is just icing on the cake. You don't have to worry about this in the introductory linear algebra course that you're taking right now. But maybe in a future more advanced course, you will actually perform that simultaneous diagonalizing algorithm. Okay, so this is again one of our longer videos. So thank you for watching and thank you for your patience. So this is True Socrates signing off. And until our next video, I hope you enjoy the rest of the day.